Hello, I'm Rob Schubert. I'm here to discuss the practical use of stress strength models to develop specifications. This is through Ascendo Reliability. Fred, thank you very much for having me come here to present. I'm going to turn off my camera. And you can just chat in the questions window. If you have any questions, I'll try to get to them. Okay, agenda. I have an introduction, target setting, and predicted failure rate, stress strength basics, a nozzle attachment strength with single comparator with Excel and ReliaSoft, brush attachment strength with 8 comparators, cable pull with both ends, 3 comparators, and then questions. So inputs for reliability target setting. So you need to, this is not an exact science, I want to say, to start with. Let me close this window, I'm sorry. So in the company I was working for, we had a certain warranty target that we wanted to achieve. In this example, we'll say 3% for a 2-year warranty period. And then that can be used to do a cascade of targets. So what we did was we took a DFMEA type of thing, or return percentages from historical models, and we built up a specific failure mode target for this particular product. You take the percentage of actual returns and historical data, and that goes into your target. It's not an exact science, though, so it may need some negotiation. Sorry. Okay, so then in this case, let me take an example of what this is, like a vacuum cleaner, not the actual example, but I'm going to use that one as an example since it was pretty similar. You might have some failure modes that you've seen from returns, such as a clip break, a brush break, a battery failure, et cetera, and those percentages, you might be able to calculate those from manufacturer quantity, take the number of returns, divide by the manufacturer quantity to get a percentage. And then for this target cascade example, you would just do either a blanket reduction, or you might focus on specific actions that you might be looking at. So say your battery failure is always going to stay the same, you would need to not put that in your cascade. So in this case, the specific actions were like to improve the clip strength, improve the brush strength in your specific actions. So you would have a different target percentage, and then that would have to total up to 3% in your cascade of targets. So to convert a target percentage to a stress profile, you need to pick a comparator or several within a similar or identical use case. So this case, you would have a vacuum that was in the field, and you would need to learn the strength measurement, the failure modes and percentages. So from your field use, you take the failure mode and percentages that we just looked at before, and then you need an assumed stress distribution to create a stress profile. In this case, I'll get into a specific example so we can look at how that is done. So you need to use the stress profile that we're going to create, and then use the new product strength measurement, and then calculate the predicted failure rate. So you're taking field data, you're creating a stress profile, which I'll show you further detail later, and then we're going to use that stress profile to calculate how well our product is going to do in the field, our new product. Or you could calculate target strength. So you could say, use the stress profile that we just created and choose a percentage failure mode, and then calculate the target strength. So you would say, okay, I'm going to design a new vacuum cleaner for the nozzle strength. It needs to be X number of pounds based on what we've just studied. So we'll get into stress strength basics. Now, when I say stress, it's not the engineering stress of force over area. It is a generic stress of force applied in the field. And strength is the forces that a product can withstand. So you're going to do, when stress exceeds the strength, failure occurs. Now, this is done on a statistical instance. So you may have units that don't see a certain stress, and there's units that don't have a certain strength. There's a distribution, obviously. So most reference materials show this type of graph, but it's not really what you need to think of when you do a stress strength calculation. This is what they generally show. You have a stress, let's say, that has a distribution that's a normal distribution with a mean of 12 and a standard deviation of 1, and a strength normal distribution of mean of 15 and a standard deviation of 1. And then you would multiply the two, and you would see that this thing would be 2.97%. It's kind of close to what you would get out of ReliaSoft, but it doesn't exactly match up, and so it makes you wonder what's going on. And then you take it and you say, well, what if I take that stress and make it above the strength? I get the same answer. I get 2.97. So therefore, how could that show what you're looking at? It doesn't. So this is not the correct type of graph. Multiplying the two probability distribution functions yields incorrect results. What actually happens with the actual correct graph, let's say you take that normal distribution, which is a PDF of the relative likelihood that the value of the stress would equal that force. So that's an instantaneous each force number and a percentage that goes with that. If you take the cumulative distribution function, the likelihood that that value of the stress that would be less than that force, so this, in this case, we're talking about the stresses in the field, you really want to look at 1 minus the CDF. So how many, let's say, how many nozzles will see 0 pounds or 5 pounds in this case where it starts is 100%. In this case, 7 pounds, 100%, 9 pounds, 99%. You get to 11 pounds, we're talking 80%, we'll see that. So that's the correct graph, this white graph. So if you use that in your stress strength graphs, it looks like this, and the calculation comes out correctly. So 1.69, I believe, is the number for a 1 minus the cumulative normal distribution of the stress with a mean of 12 and a standard deviation of 1, multiplied by the strength, you get 1.58. Now I'll give you the actual, I'll show you the calculation. But if we take that stress and we say slide it to the mean of 18, you would see that 98% of the product will break in the field. So this is the correct view of the graph. You don't want to look at the other graph. This is more appropriate. So this is, you can do on an Excel spreadsheet, which is my favorite way to do it. But you enter a force in pounds. So this is just a list of numbers, and so as a integral, and this is an integral we're talking about, the smaller the difference between each of the numbers, you get a little bit more accurate result. So in this case, I'm looking at 1 pound up to 7 to 8 pounds, and then even go to 0.1 pounds after that, so that I can get a little bit better gradient as to this calculation. And then we put in that 1%, 1 minus cumulative distribution, which is a function that you can get in Excel, which is a normal distribution. And you can see up to the right here is the integral that we're looking at with the stress times the strength times the dx, which will be the difference between the forces. And then we're going to enter the normal distribution of the strength, which it's a stress level because we're using the stress level to calculate the strength and basically where we are on this graph. But that is the strength. So we take the strength mean, the strength standard deviation, and we're not doing cumulative, so it says false. And the true up here does the cumulative for Excel. And then you can actually use any distribution, gamma, exponential, log normal, Weibull, etc. Every function, not every function obviously, but most every function is in Excel. So then what we do is we multiply the two, stress times strength, and then the delta in stress level, which is 1 or 0.1, depending on what you're looking at in this graph. And then what we do is we sum that entire column and we get 1.69 like we had before. So this is the nodule attachment strength example. The goal is to find a specification for the nozzle attachment strength. Units would be returned with broken nozzles, no explanation. Again, I had changed this from a different product, but similar idea behind it. Now note that the test method doesn't necessarily have to be identical to the field method. We're trying to do strength in a test method of products in the field. We're going to use that strength to calculate the stress from the field, and then we'll use that stress with this strength of the new product to calculate what that return percentage would be, or we're going to use what strength you need to get out of your product to achieve a certain percentage. So the test method should be related, but it doesn't necessarily have to be identical to the field failure. This is sometimes a big trouble for people to understand outside of reliability, but this is how it would work. So in lieu of better measures, the simple return rate versus manufacture date can be used for decent estimates. This is how I was talking about our failure mode percentages. Return total divided by the total manufactured. Use mature data. Obviously, you don't want to say, oh, our newest product has no returns, or has 1 return for 1 million shipping. If it's not mature, you're obviously going to get a wrong answer. So you need something that's been in the field for a while. For this example, I'm going to use 0.78 for a 2-year warranty period. So is there an overall target? So we're doing a specific target. We used failure mode and a return rate target. What are we expected to have? In this case, I'm doing a rough estimate. We looked at that 0.78 and we're saying to ourselves, that's probably what I would call the line between good and borderline. And I work with the team and I say, where do we want to be? It's not something I can do in a vacuum. I'll need to work with the engineering team and try to develop this particular percentage failure, or failure mode percentage. And so we came up with this together in a group. It's rough, but if we all agree on that this is the way we want to do it, then we can learn from it. We can decide what we're going to do with the results, et cetera, et cetera. So the current shipping nozzle, we did a measurement in that test where we pulled up on it straight up and we broke it. And in this case, we're looking at an average of about 21. So we'll use that mean and standard deviation from the actual measurement, and it does fit the Anderson-Darling test, says that it is normal. You may find that a different distribution might be more appropriate. This does look heavily skewed to the left, but it still says it's normal. So we decided to go with normal just for simplicity's sake of the understanding of the particular team. You get deep into different distributions and you might find that you get into esoteric arguments that you don't want to get into. So we used a normal distribution, and everybody understands that in engineering for the most part. So what distribution to use for stress? So this is another reason-based approach to what kind of stress you would see. So we're going to assume a stress distribution. In this case, we didn't think a normal distribution was appropriate because we had random forces applied to the product in the field. A small force, you would say, would be way more often than a large force. So in most of these cases, like 0.1 pound would be applied very, very often. 1 pound might be applied pretty often. 10 pounds might be applied rarely. 20 pounds, 100 pounds, very, very, very rarely. So they generally occur continuously independently at a constant average rate is what we thought. And that is the definition of an exponential distribution. So we said that the same forces would apply to each product in each use case. So we're doing another vacuum cleaner with another nozzle. And so those forces are assumed to be the same. So a different user would apply probably the same type of forces to that nozzle as other users and other vacuums. So it's one of those things where if you have a significantly different product, this may not work, but for the most part, this is where you'd have to start. So what we have in the stress, we have one variable, and that's lambda. That lambda we're going to calculate from our field data, and we're going to use it as our stress distribution. So in this case, we're using a goal seek, which is a function in Excel. You just go into the what if analysis and you select goal seek, and then that will show, and you select the sum, which is 1.69 here, and a changing value of lambda, which is where I put up there above the stress column. That's just refers to that particular column for lambda. And we're going to set that to 0.78. That's what we said our field rate was. So when we do that and we hit goal seek, it cranks through attempting to find the value that will satisfy 0.78. When we do that, we can get to that result. In this case, we get 0.22 as our lambda, and that becomes our stress profile. So when we integrate the two, and I had to use a different graph because obviously the stress profile is, or the strength resultant is much smaller than the stress profile. So it looks kind of like a flat line when you put this graphs together. So I put it in a separate graph, but we're looking at 0.78 when we integrate that. So then we find, we're going to see what our current new design is. So we've got a new strength measurement, and we're going to use the same distribution since it's a very similar design. And we find that our median, or our mean, I suppose, is 15.1, and our standard deviation is 2.2. We're going to crank that into this graph. So as you can see, the pink line is our new product, which is not performing as well as our old product. And we do the multiplication of the stress and the strength, and we get 3.8, which will consider ourselves unacceptable, and we need to go back to the design and back to the drawing board. This can also be done in ReliaSoft. So ReliaSoft has this exact same calculation. You don't get to see all the guts that Excel you have to do with Excel and your own. So you can input the strength measurement and the assumed distribution in life data. So you add a spreadsheet called nozzle strength, and in this case, it's nozzle strength, and then a stress spreadsheet, and then you can actually the stress in this case, I'm putting in random data. So I put in something that looks close to a exponential distribution. As you can see, 12, 8, 6, 5, 4, 3, 2, 1. Not really that important to look like anything whatsoever, but it needs to have something to begin with. So then we change the distribution and graph the normal distribution, and we change the distribution to the exponential and graph that, and that will get you two distributions, and then you can plot the two to add a stress strength comparison where you have the stress data 1 and the strength data sheet 2, or data 1 under nozzle strength, I'm sorry, and then it will graph it. So it graphs it traditionally, is what I say, when it should actually go up to a cumulative distribution would go all the way to 1. 1 minus the cumulative distribution would go all the way to 1 for an exponential. So these are the two graphs. I've got an exponential in black. I have the nozzle strength in green. And then we can move on to creating what is the target reliability parameter in this case. So we're developing the stress profile. Start the target reliability parameter estimator, which is this button, looks like a target. And then we enter the target reliability. Remember, we had 0.78 was the percentage, and we need to use the target reliability, not unreliability. So we subtract that from 100, we get 99.22. We enter that, and then we hit calculate, update, and then we transfer the parameters. And then that will get your lambda of 0.2265 is what happens when you hit the calculate button. And what we're going to do is we're going to use user modified results. There's a screen to pop that button. And then we put in our new product data. Recall that we had a distribution of the new nozzle. I typed in all those numbers, and then we hit the reliability of said new nozzle, and we get 96.22, which is 100 minus 96.2 is 0.38. So we're looking at the exact same answer we got before. So it can be done in ReliaSoft. Not my favorite method to do it because I like to see the guts. And again, we're looking at our unacceptable result here. So even with the best data, sales spikes, return delays, people who don't return can cause percentages to be out of whack, I call it. Even then, what is returned is likely to be a sample of overall totals. So if we consider that both the returns and the force data our distributions based on a sample, we can actually improve the accuracy of the profile. This can be done if we have more than one product. So in this case, I have 8 vacuum cleaners that have a return percentage of the nozzle strength, and we looked at all 8 of them, and we said, okay, what's that return rate? And you can use that to decide what maybe best in class, good, borderline, and unacceptable are. So we're pretty similar in where we landed with unacceptable on this one, but we kind of moved the borderline good line up a bit, and then best in class we decided was 0.1 to 0.25. So now we've got another step where we call best in class, and then we have what is it, 8 vacuums here with different return percentages of that particular nozzle strength issue that we had. And we've made a new target. So now my stress profile is going to be the same across all 8 products. And you may guess that one specific point number is not going to make all the percentages equal exactly what we found in the field. And that's what I say when I say errors. So certain models in this case were cheaper or more expensive than others. And so you might guess that those different price points might change what the customer does. So if he buys a really cheap vacuum and it lasts for a year, he may just throw it away and buy a new one, and we would never see that nozzle breakage return rate. Or the same guy or the same similar customer might be, financially strapped, bought a really cheap one anyway, and then it comes back and or they're really adamantly about trying to get their warranty repair. So maybe you may have more returns for a cheap product, or you may have less returns. I've never personally found any reason to believe either one. I'm going to use statistics to develop the stress profile. I'm not really sure I need to get into the psychology of the customer to get the answer that I need. I'm going to use statistics instead to try to find the stress profile based on 90% confidence bounds of all 8 returns. So we have return percentages we're going to do confidence bounds on, and we're going to do force data with confidence bounds. So as you can see the calculation here, we have a lower limit and upper limit for the percentage returns based on the number of quantity of units. And then we have upper and lower bound on mean and standard deviation of that nozzle strength. So we can actually do this in Excel. I'm not going to get too deep into these calculations, but we have a lower limit that is an F distribution based on what is a percentage. So percentages have a lower and upper limit that we can calculate. And then we can also calculate the mean and standard deviation in Excel with the confidence intervals of those products. So here are the return percentages, and then we have a lower bound and an upper bound. We had pretty good data, so they're pretty tight, honestly. In some cases, they're a little bit larger because some sold more than others. In vacuum number 3 is our 0.78, has a 0.28 to 1.4 percentage return rate. And then our force data has means and standard deviations, in several different locations. Designs were different for various reasons. And you have upper and lower bound. These seem larger. Hard to compare the two, but they are larger, in my opinion, between the return rate, because the return rate we had, thousands and thousands of units. In this case, we're measuring 10 nozzle strengths. So Excel has a solver, and the solver is a more complex goal seek type of thing. So what will you minimize? So we have, we need one answer to minimize. And so we want to minimize some sort of error between these 8 vacuums. Then we have to decide how to calculate that error. It needs to be one single number. So I would not recommend weighting any samples differently than others, any vacuums different than others, but there's going to be 8 products, and we'll be able to decide perhaps maybe what forces are the lower and upper bounds, or the upper and lower bounds of the percentages. So you're going to guess that some of them are going to be perfectly aligned to the lower bound or the upper bound of each of these to try to fit itself into a error. So then I put in these confidence interval limits with a reasonable lambda. Also needed to be, there needs to be a constraint on that. There's a lot of different things to fiddle with on the solver. There's other solver options like the constraint precision, the convergence, and then maximum time without improvement. I found that it won't get very good answers if you let it run for a short period of time. So that was one that I really needed to expand. And sometimes I would run this one overnight on just a regular PC, get an answer in the morning. So the error, kind of have to normalize the error. So we had 3 parameters being adjusted: averages, standard deviation, and the total failure rate percentage. They needed to be normalized so the solver could reduce the error equally. In my case, that's what I wanted, equal error. I wanted to set the weighting. I didn't have any weighting. You could decide that something needs to be weighted more. It would be measured as a distance from center point. So your center point, your ABS absolute value of the solver estimate minus the center point, the bound minus the center. So you're taking, in this particular example that you see here, it is -2 from 0, which is our center point, and our bounds are -4 to 4. So we take -2 minus 0 divided by -4 minus 0, and we get a 50% in this case. And that's what I considered the error for each parameter. So I had an upper and a lower bound that was those parameters that we set before, the confidence intervals at 90% for both the percentages and the mean and standard deviation. So how is centering determined? So you could either do linear or least squares. So least squares gives more weight to things that are outside of the bounds. As you can see, a square, let's say X square graph is the red graph, and a linear graph is the blue graph in this. So when we get further and further outside of 1, which was 100%, let's say, then it considers that more egregious kind of situation. So, but I found that you would get a lot more errors that were, 50%, 10, 20, 30, 40, 50 were not weighted enough, in my opinion, when we did the least squares for anything less than 100, because we're talking about a square of like 0.1 and such. So I used a combination in this case. So I said if it was less than 100, I'm going to use linear. If it's more than 100, I was going to use the least squares. So so I could get it to focus, bring it in more when it was less than 100, and really focus on the ones that were outside of the 100% error. So it was like missile command. So you're trying to hit everything, and I don't know if you've played this video game from the 80s, but it's like trying to save your cities at the bottom by doing your best to, and maybe you need to target just one or whatever, but keep it from destroying your cities. So this nozzle strength example, when I did the solver overnight, you can see that the error column where we have the return percentage, we're seeing vacuum 1, vacuum 2, and vacuum 3. When we get to the return percentage, what I called the error was 98 to 69 or 46, 69, and then vacuum 3 or 4, 5, vacuum 4 and 5 were over 100% error. So it was outside of the return percentage bounds. As you can see, the model estimate is the column that we would compare to the upper and lower bounds of the return percentage, and you see that vacuum 4 and 5 are outside of those bounds, and as well as vacuum 8 is outside of the bounds that we set with our 90% confidence intervals, and everything else was inside the bounds. So it's not obviously not perfect. We can say possibly there's something special about vacuum 4, 5, and 8 that that is maybe different in how it's returned, like I've discussed before, on how things are returned, or it's just a sample issue, sample size issue, etc. And then when you look at nozzle strength average with the error, you can see that everything is within the bounds. So I think I hard coded it that it needed to be in the bounds in order to solve. You can force it to stay inside bounds. And then also the standard deviation, I had forced to be inside the bounds. So everything was in the bounds, and you notice that the standard deviation mostly have 0% error. So they're set specifically on the center point of this of the point estimates for standard deviations that we saw from the test data. Maybe that's not exactly what we want, but you can fiddle with these different things. Nozzle stress distributions you can see on the left with the new lambda that we solved for. So we found the lambda to be 0.233, and you can see on the right there's a failure rate calculation. So those are the little bumps that you get when you multiply the two together. So if we, in this case, I wanted to make a target for a specific product to achieve I'm sorry. We wanted to set a target strength for a particular product. So in this case, we are looking at best in class being a 0.25 maximum, and then good borderline, good is 0.5, borderline is 1, and unacceptable is above 1. So the upper limits we're going to calculate with the 0.233 lambda. We're going to calculate what the return rate is based on a certain strength. So we've developed the lambda 0.233. Now we can use that in a stress strength calculation to find the average and standard deviation. Now it's two parameters, it's two variables, one equation. And we know that that can't be solved empirically. So we have to choose, say, a standard deviation in this case, and then we can calculate the average. So I chose a 0.1 standard deviation. If we look through the standard deviations above, it seems reasonable to be about around 1. There are some that are less, there's some that are more. You could argue a different number. This is what I had chosen. And then you would have an average calculated off that. So best in class is 26 pounds, good is 23, borderline is 20. So the engineer can design to 26, 23, or 20. So even more complex model. So you can even get deeper into this. In this case, we had a power supply that had cable failures at each end, and we wanted to decide, what broken cable percentage rate we had, what strength we needed. There are 3 power supplies that had significant field data, with mature data, and we could test those. So, sorry, okay, next. The return rate for broken cable. So our service department gave us information on broken cables, and oops, I forgot to change that from LOF to PS. Okay, so PS1, PS2, PS3 were the had return rates of 0.45, 0.07, and 0.13. And then the verbatims, which are what the service technician would enter into the field of a free field, basically. They said that it was the wall end, or they said it was the plug end. They're very uncommon for them to say wall end. So we looked at that and we saw that power supply 1, 2, and 3 had a very, very low rate of that, but a lot of them were completely blank. So we didn't have really good data on the wall end. We said that if there were any that said wall end, then it was definitely a wall end. So that would be our minimum percentage at that end, and our maximum percentage would be all of the return rates. Return rates due to cable. So in this case, we had percentage of total returns was 15% for power supply 1, 2, and 3. And now we're setting our target here. So we said, okay, best in class, let's do 0.5%, and good was 0.1%, borderline was 0.1 to 0.2, unacceptable was a great point above 0.2. So if we took the cable return percentages, which is 15% of a 1% total failure rate, and then multiplying 15% by 0.1 or by 1%, and that's how I'm getting these a lot smaller numbers. So if we said that total cable failure rate should be 0.1, then we're looking at good in this case. So we had to measure the strength of each product, and there's tools out there to measure strength. Pull each end to failure. So we're pulling each end to the failure point. And then we're going to calculate those limits. So we have a pull force of the wall and a pull force of the connector side, and we calculate, we measured 10 units, I believe, and we have a point estimate of the mean and the standard deviation of the connector side and the wall side. We calculate the lower bound and the upper bound the same way we did before, with the equations for 90% confidence intervals, and then we have a return rate that is also has upper and lower bounds. Now, a lot of people wanted to talk about, was it cyclic or was it a specific strength where you do pull to failure? And you could test, say, X number of pounds for a number of cycles. In this case, we decided to do a pull to failure to equate back to a cyclic pull strength. And so, we looked at, SN curves, which basically tell you that you would see that these are related. And again, that's why I'm saying that the test should be related to the failure, but doesn't have to be exactly the same as the failure. It can be kind of a surrogate. So a stronger cable that holds, say, 20 pounds should take 10 pounds of pulling on it 100 times, might last longer at 10 pounds than, say, a product that has an ultimate strength of 11 pounds might only take a few pulls at 10 pounds where it would break. So we're using an ultimate strength instead of a cyclic strength, and they are, interrelated. Our assumed distribution, again, is an exponential distribution because, once again, it's random forces, stresses applied in the field, and continuously and independently at a constant average rate. Again, an estimate, but it is still seems appropriate in this case. We assumed same forces to each product in each use case, but we decided that the wall end could be different than the connector end. Let's say the wall end is attached to the wall, so you might find that you're pulling, maybe the most of the damage occurs when somebody just yanks it out of the wall from the cable. I've done that myself. I shouldn't have done that, but I did. And then the other end might be connected to a gaming console or, say, a phone. And so does that get pulled more? Maybe more, maybe less. Let's just say different. And that's what we want to say, that we're going to have two different exponential distributions for each end of the cable. So then we use the solver again to do a wall stress profile and the connector stress profile in two different lambdas, and we get add both of those together to get the total return. And so we do the wall cumulative stress force, 1 minus the wall cumulative stress force times the wall strength, 1 minus the cumulative stress force of the connector and the connector strength to get a total failure rate. In this case, we did that. We did the solver. We found the wall was 0.95 lambda and the connector was 0.31 lambda. And then at that point, you can compare the stress profiles, and you'll find that, here's these three with the strength versus the stress profile. We find that the PS3 has a bigger overlap than, say, 1 or 2. And then we can look at the failure rate distributions. In this case, we found that the total failure mode calculated was kind of outside of the bounds for power supply 1 and 2, inside the bounds for power supply 3, just on the on both ends actually. That was the total percentages. We did a calculated wall end to be 0.003 on PS2 and 0.002 on PS3, where the calculated connector end was a lot higher on 1, 2, and 3, which makes sense in this case. We felt like that particular one was getting more stress than the wall end. So we're going to compare that to the targets. We were going to create the target strength. We had chosen a standard deviation of 3. If you look at the distributions, that was pretty generically good. Average, I guess, average standard deviation. We take the wall and connector end and try to do a total of 0.5. A predicted failure rate would be 0.035 and 0.016% for wall and connector, and so anything above that was going to be what I call best in class. Wall end for good was between 12 and 12.5, connector end 22 and 24, borderline 11 to 12, wall end under 11, connector end under 19. Those were unacceptable. So in summary, we had pull comparator product failure modes and rates. We needed to pull the comparator product failure modes and rates, and then set the specific failure mode targets, choose an assumed stress distribution, measure the strength of the comparators, calculate the targets or predicted failure rates. So we were taking field data, calculating that stress profile, and then returning it to a target in both examples. And then once you get to the final product that you have and you can actually measure it after they built it from the targets, when you measure it, use the true mean, the true standard deviation, and then you can calculate your return failure percentage. And you could use confidence bounds too to try to determine if your sample is maybe it's still causing it to be measure higher than or lower than what you expect. This is about me. Rob Schubert. I was working at Shure for 13 years. I worked as a black belt and at Ford Motor Company, quality engineer, black belt, noise and vibration engineer at Ford Motor Company. I presented this very similar to this one in ARDC. I had some other presentations at ARS and Minitab Insights. We also did the overview of reliability functions and life testing in Minitab. That was done with Fred and Ascendo Reliability. And that's pretty much everything. Let me know your questions.
Yep. Hey, Rob, looks pretty good. The questions tab is looking pretty quiet at the moment. We'll give folks a moment or two. When I first saw your slide deck, I was like, wow, that's a lot of material that you covered it. I know some of it's pretty quick, and you do rely on some of the feet like Solvit or Solver and some of the tools in Excel to make this happen. So we might have to have you back just to talk about how to use Excel to do this stuff in a bit.
Yeah, yeah, it's deep in Excel. That's one of the. I mean, when you think about computers and what they're meant to do, like a solver is one of the things that you think about. Well, I need it to calculate something, and this is the best thing. I found that the solver is actually a third party outside of Excel that I guess they hired somebody to create the solver, so it's in there. A lot of the functions, like I glossed over a couple of tabs there, those are complex and not very well understood by me. I dug deep into some of the documentation, but still came out not really understanding all this, how the solver works exactly.
Hmm.
And so a lot of my stuff that I just covered, I had to like pick different parameters and just see what happens kind of thing. Sometimes you come up with something that's like way off or it solves in like 3 seconds and you're like, are you really solving this or what? and and so I went through a bunch of different different ways that it does, and there's like an evolutionary and there's some other linear or something or other um, parameters that you can set, and it goes through and solves it. So but the biggest one was the time, and it liked to cut off in like 60 seconds or something, and I'm like, that's not even close to getting to what I want it to do.
Hmm.
So you can even see it calculate through it too. So if you set that flag.
Well, it's a powerful tool. There's no doubt about it.
Yeah.
Another question I had for you is on the force of being applied. Like on the first example, you had the nozzle of that vacuum. Um, and I've made similar assumptions in the past when you really don't know how the user is going to use it, but you can imagine that sometimes they're just going to set it down on the ground and it's going to tap, and you can measure that. You can put a force sensor there and you can measure how much load it's taking. Other times they drop it, for example,
Right.
and it takes the full weight and you can measure that. Did, I mean, in those circumstances, I mean, the first guess is just, well, like you said, expect most people to just touch the ground and it'll be a light force, and that'll happen a lot more often. And then when you hit it harder, it'll be much more, or it'll be less often that it occurs for any particular user. And there's variability among users. And so it's just a simple exponential decay of the load that it'll see is a first estimate. Now, I always start with that and get a first pass at it, and then go measure it. Is actually get different people to, you know, do a light touch, do a heavy touch, do what you think is too much of a hit, and get
Yeah.
some measurements for it. And then
Mm-hmm.
it's back to the envelope of, well, how often do you expect these different amounts of hit or force? And the best is I had one example where we brought in real customers, and it was to test out different features of the software system that was being used, but we're using hardware to do it. Um, but we could measure their use of the hardware. And so we could
Mm-hmm.
get grip strength and things like that. And we got actual measurements. Now it's a little artificial, they're in the lab, right? It's not at
Yeah.
home or in regular use. It would be really expensive to sensor up a bunch of vacuums and send it out to 1,000 people. But in some cases, you need to go do that if it's
Right.
a critical question. So
Right.
anyway, just a thought.
Actually, as I said, I changed it from the original. The original was not a vacuum cleaner, but it was a lot smaller product.
Well,
Um,
the
and
concept
it was,
applies, though, right?
yeah, I was going to say that it wasn't really easy to measure this particular nozzle on this thing is, the size of half an inch basically.
Yeah,
In any, like the only thing we could do is like, do a specific test, like the force test in this case. Made it really hard to see like what kind of forces were applied. And then there was torques that were applied to this nozzle.
mhm,
There was drops, there's all kinds of different forces. We decided that, let's simplify it, find the strength of the nozzle in this case, and then measure it the same every time, and hopefully that would relate to, and it kind of, like the ones that had the higher strength had a lower return rate. And so if you can see that correlation between the two, maybe that's good enough.
yeah,
Like you say, there's I've done a lot of studies that were like human factor studies, how much torque is someone going to put on this knob so that you could do a certain test with reasonable forces. Yeah, that's a big thing. Human factor studies are very important, I think, for these kinds of tests.
Yeah, and he gets pretty creative. All right, we got a couple of questions. Nelson's asking, how do you think about the choice or setup of tests to the, I think FM is failure mode of interest. Usage, abuse profiles can change a lot. And I think you just talked about that a little bit.
Yeah,
Is if you can measure it, that's great. If there's tabulated data, that's great. If not, it's back of the envelope in engineering judgment.
right. And like as I go back to if you can say that you have multiple products, and this is a lot easier with multiple products, if you can do a force measurement that has, strength relate to the return percentage, where the high return rate has a low force and vice versa. If it correlates like that, then I feel like you've got good enough information where you can actually, get through this particular process the way that I showed.
Yeah. And Thomas is asking a similar one. If you're guessing the stresses and I've had two examples in my career where one of them was a client of mine was making a handheld. It was the little device that the baggage handlers at the airport use to scan bags that they put on or take off of the airplane. So it's on the tarmac. They're throwing bags around. These things get dropped all the time. So they rightfully thought, well, drop testing's got to be something we got to worry about. So their initial design of the initial product with no field experience, they went to the standards and it said drop it 10 times and randomly, and they got it a design that would not have any failures after 10 drops onto concrete from I think 3 feet or something like that.
Mm-hmm.
It got to the field, it was a disaster. Like 30 of the first 100 came back in the first week.
Wow.
Right? Or some, and they said, well, let's go to the airport and see how they actually use it. And they're dropped, they're run over, they're thrown, bags drop on them. And it's like, okay, yeah, now I see how they get dropped 40 times a day and from 6 feet or higher.
Yeah.
So they said, well, let's drop it. Let's make our next design 6 feet and 20 drops. And then they got a little better. And then they started watching the correlation as they rolled these things out to different airports. That the last night, make a long story short, they were at like 24 feet and 100 drops. And they're still seeing field failures due to drops in the field, but very small numbers. But the design initially was the standard. And when they first thought, well, that we got to go higher than the standard, they had so much pushback. Well, we don't know how they're dropped. So sometimes a trip to the airport saves it. In another case, I was working with Hewlett Packard when I was working there. They would, on a regular basis, they would instrument 100 or 1,000 inkjet printers, and they would ask customers to use that printer, and they would give them free ink as an incentive, and allow HP to collect that data. And it had temperatures, how often they printed, whether it was color or not in color, all kinds of different parameters, but including the stresses, like how often the printer was moved. The little accelerometer shows how much vibration it saw, and so we got scads and scads of data, and some of it was pure marketing stuff. Some went to the printer nozzle people, some went to us making the mechanism to understand the stress profiles that our printers were actually seeing in North America. And that would go back into our design guidelines saying, well, it's going to see this much vibration, but we would have instrumented data that said, here's the profiles we see in normal use. Here's how often they're moved, here's how often they're dropped, here's how often they're loaded with new paper. You can imagine instrumenting 1,000 printers and distributing them and monitoring them for a year and then doing it again with the next model is really expensive. And not every company can afford to do that, but the data was invaluable for the design teams to figure out how to make a robust printer.
Yeah, definitely. That would be definitely really good data. I know cell phone companies can sometimes get that data too, how
Hmm.
often the accelerometers are right on there, so you can get that data
Yeah.
immediately.
And I hear that Tesla has a lot of telemetrics or telemetry that comes back from their
Right,
vehicles. So they get a lot of info. It can be done. It has to be worth it though. So part of it is
right,
knowing what failure mechanisms you need data for, which ones are causing you problems or expected to cause problems. And sometimes you just do it in the lab, right? You bring in a few people and try it and try to make some
right.
of it.
Yeah, like the instrumentation of a whole printer seems like you'd have to need the entire engineering team on board and have everyone uh, be able to, yeah, like you say, it's expensive, so you need to have the financials behind you, and that's probably the dream situation for most reliability engineers to get that kind of information, which is, most of the time it seems like we're given little resources to complete some of these things, so do the
Uh,
best you can.
well, it's often more like your last example where it's you don't know which end of the cable is having more problems, and then it's such a low cost item we don't even get them back, right?
Right,
They
yeah,
just throw it away, and
yep,
so you
yeah.
really don't know. So,
Mhm.
all right. So I think those were the couple of questions. We're a few minutes over. Let me thank you, Rob, for bringing on this presentation and the previous one. And as I've mentioned offline, I hope to see you back again. And we'll look forward to having you back with the Ascendo, either with some courses or with some more webinars or both, or, whichever works for you. So
Cool.
we'll talk with that. All
Yeah,
right, Rob.
thanks. All right,
Thanks
see ya.
again. See you later. Have a good day.
All right, you too.